So am I in this picture? I think so. You know, what I'm constantly trying to do in this class is get some idea of perspective. I mean, I'm more interested in telling you 1,000 times how big the universe is than explaining very much in it. I'd rather have you get how big the universe is. What does give me a sense of this is this new discovery. It was discovered in the sense that it was published on January 7th of this year, and it was discovered by at least one woman and maybe two, and the name of the thing they discovered is the Radcliffe Wave, named for Radcliffe, part of Harvard, which used to be a girls' university, women's university. The Radcliffe Wave is something that is close by. We never saw it before. It's right there in the sky. We just didn't see it because we didn't know it was a thing. We thought that they were things. We could see them, but we didn't know they were part of a thing. The thing that they are part of is a wave, and that wave is 40 quadrillion miles long. That sounds like a big number. 40 quadrillion miles long. It is 9,000 light years long, and it's right next door, and we've never seen it before.
What's it made of?
It's made of stars and gas. Thank you for asking.
Right there, don't we see the stars?
We see the stars.
Oh.
We see the stars. The thing is, if you see the stars in the sky, the thing that you don't know about them is where they are. They're there, but are they close or far away? So if you don't know their relationship to you in terms of distance, you don't know whether they're part of a grouping or whether they're just independently, lined up in some way. So we couldn't see the lineup. Now we can. This is a movie of the Radcliffe Wave. Moving away from the sun, away from the nearby stars. Now the stars are all moving in because they're moving away. That's the galaxy. That's the Milky Way galaxy. And that is the Radcliffe Wave. And now they're going to be turning to give you a sense of it in 3D. Now it's a line. That's our sun. That's our sun. Giant wave of gas.
Are they considered to be part of it?
In the sense,
You ever feel like you're being held back?
a wave. The word wave is a funny thing. You kind of know that you don't get carried by a wave unless the wave is breaking. You kind of know that waves pass past you. They move past you. But so the thinking is that this wave, we were part of the wave, and now we're not. So we could possibly be not only part of the wave, but this wave could have been involved in our own creation. That's not necessarily a theory at this point. Point is, we were created that's a terrible picture to leave on the screen. We were created in a cloud of gas and dust. So there's the way. This is the Milky Way. This is the Milky Way. This is the wave of gas and dust. That's us. The wave may have passed us by, and in the process compress the gas clouds that created us. Let me give you a picture of the wave, because I control this. See, this is now, the video you saw was made by using this software that I'm currently manipulating to play with it. So you can literally make it disappear, because it all goes right down the tube. Or you can see it as a wave by seeing it like this.
Are there other known waves in the galaxy?
Well, the thing is, no. The galaxy itself, the arms of the galaxy, are considered by some people, many people, to be a wave moving around the galaxy. So, if you will, all the arms of the galaxy are really nothing else but waves that are passing through the galaxy. That all could be nothing else but a spinning wave. The stars don't move at the same rate that the wave does. The wave moves faster around the stars go around the galaxy, but so does the wave. And the wave doesn't travel at the same rate as the stars. So I think what you're seeing here is literally waves. But the difference is that what you're seeing, this is an artist's conception. This is what we think the galaxy looks like. We don't see this. This is all made up. What we do see is this. And why do we see this? Is because the GAIA satellite that recently released its data, that, a thousand astronomers got the data at the same time. And when they did, they were ready for it. They took all the data, they put it into their software, they pressed go, and a few months later, they got themselves a wave. These people found themselves a wave in the galaxy. There's a lot of stuff they're finding in the galaxy now that we can see for the first time what is nearby. Because we can't see, with GAIA, we can't see beyond here. We can see a little bit out here if the stars are bright, but mostly we can only see here. And so here is where we're learning a lot of stuff. And then, of course, we're going to say, well, if this is true, then that is true. But it's by extrapolation. So the thing is, what is this? What is this thing made of? And that's what I find extraordinary. I have been for many years doing this particular demonstration. This is a particular piece of software which allows me to explore the solar system and the galaxy and even the universe. So at this point in this software, because I've readied it for display, at this point in the software, I'm pretty far out in the galaxy. The sun, which is right here, this is the letter S. I'm going to pull out, and the sun is right there. And you see it's getting smaller. And I'm pulling out farther and farther. All the nearby stars are zooming into the center. That thing off to the right-hand side that looks like a bulge of some sort is a bulge. And see, we're right there. We're right there. I'll make us more visible for a second. We're right there. That's us. Now I'll turn us off. Well, we're right there, and that was a little concentration of stars. But the reason, so this is the galaxy, the imagined galaxy, and that thing in the center is a wireframe of the bulge that sits in the center of our galaxy, because this particular demonstration makes our galaxy look like a plane. So, in fact, it's completely flat. And so they put a wireframe bulge in there. And you can see these are our stars nearby, right there. Okay, I'll make this visible again. We're there. We're there. So I've done this many times, and I've shown people, yeah, that's where we are, and you can see we're kind of in a spiral arm or not. You know, there's a spiral arm, there's a spiral arm. We seem to be in between two spiral arms. And then sometimes in this class, because I've been doing this for a very long time, sometimes in this class I press this button. And this button suddenly lights up something in the sky. And the thing that it's lighting up, I'll go zooming in on it a bit. The thing that it's lighting up is something called Stellar Nurseries. Stellar Nurseries. Wow. Okay. Now the Milky Way starts to come into some sort of focus for me. The idea that the Milky Way is not a static structure that has stars and pretty pictures and nice stuff to see in telescopes, but the idea that this Milky Way is a living place where stars are born and die is kind of amazing. And then you go, oh, okay, there's Stellar Nurseries. So Laird, thank you very much for showing me these Stellar Nurseries. Look, see, I light it up. You notice that the Stellar Nurseries are only close to us. Nowhere else in the Milky Way are you seeing these Stellar Nurseries. And the reason you don't see them is because we can't see them. So the bigger a big telescope can see here, and yes, there are other Stellar Nurseries in the Milky Way, but the majority of them are right home. So if we could get a sense of what it's like to be what things are like around us, that'll give us a sense of what the Milky Way is like. And the idea that they just found 40 quadrillion miles worth of stellar nurseries, that's pretty cool. Stars being born, not yet having left the nursery. Let me show you. Gaia itself is not a very good telescope. It's not a good telescope at all. It has a limited capability of being able to see things because it's a small telescope. This is a picture of all the telescopes on Earth and in space. These are the various telescopes that we, the human race, have. This one hasn't been built yet. This one is planned for 2022. The telescope that you all know and love from having grown up with it is the Palomar Telescope. You know, the one in California, the Hale 200-incher. That's this one. This is the one that we all grew up with, knowing the pictures which are being taken with that. The telescope that takes the picture of the beautiful sky and that we spent billions of dollars and visited many, many times to visit, that's the Hubble, and that's over there. That's the Hubble telescope. We're planning to launch a telescope in the sky that will be much bigger than that and perform much better than that, and that's this one. That's the James Webb Telescope, and it still hasn't been launched. It will be launched in a year or two. So these are big telescopes, big for the sky, big for the sky. The Gaia telescope is this small. So when I'm telling you that we're going to look and see across our galaxy, we need things like this and this to see things Yes.
Where is the GAIA telescope now? Where is that?
Thank you for that question. I'll give you that answer in the next picture. So where would you put a telescope that is designed to see not the Earth, but the universe, especially the galaxy? What you want to do is you want to get it away from the Earth. So,
That's the sun.
and so you want to get it away from the Earth. So you put it, you send it away from the Earth. You send it away from the Earth. See, this is the Earth to size. You send it away from the Earth, and you send it to some place like this, which I'll tell you in a second. But it's orbiting. Look at that. It's orbiting, but it's not orbiting a planet. It's not orbiting a planet at all. What is it doing? This is called the Lissajous figure. It's not orbiting a planet. Okay. There's the sun. There's the Earth. There's L2. And this is a diagram of the gravity wells surrounding the sun and the Earth there. And right there, as you can see, there is a inflection point. If you're sitting here, you can fall down this way, or you can fall this way, and you can fall that way. But if you're just careful, like balancing a pencil on the top of its eraser, it will stay without falling to either side of this gravity well. So what they do is they literally put this thing there, and then they have little rockets that keep it. When it goes this way, well, they pull it back. When it goes that way, they pull it back. And in such a way, the Earth is never in its way, because it's far enough away, and they can observe the entire galaxy without the Earth bothering it. And they need to take pictures of this galaxy for years and years and years, and the rest of the universe for that matter. This is called...
And they only look away from the sun.
I think they only look, they only look away from the sun, but the thing that makes this special is they can look towards the sun. If you are looking to see whether or not the Earth is going to be hit by an asteroid, and the human beings on the Earth will be destroyed like the dinosaurs, well, you certainly want to look everywhere in the sky to see if there's anything coming at you. But it's easiest to look away from the sun, because that way you don't ruin your optics. To look towards the sun would be crazy, because the sun can screw everything up. So all the cameras that are designed to find the asteroids look away. This camera, because it's far enough away for some reason in the geometry, is capable of looking at asteroids that are coming at us from the sun. You know, some asteroids will come in and do this, and we could never see them because it's too dangerous to look. But this camera can, and so it's looking for near-Earth asteroids, potentially hazardous asteroids. So they're finding some of those as well. It's not its main job, but it can do that job. This is called, these 5 points are called Lagrangian points in space. Jupiter has them. If this was Jupiter, if this is the sun and this is Jupiter, there is a group of satellites right here, asteroids, called the Trojan Asteroids. There's a group of Trojan asteroids. This is Jupiter. Trojan asteroids here. Trojan asteroids here. I'm not sure about other places. So in space, this is a very valuable place. When you want to when you want to put something in space and have it not orbit the Earth, and you want to put it in a good spot, which is safe, and you don't need to keep using rocket fuel too much. If this is the Earth, and this is the moon, if this is the Earth, and this is the moon, guess where the most valuable place in the solar system is? Right there. Somewhere between the Earth's gravity and the moon's gravity is L1, and L1 is a destination. for the human race. We were going to build a lot of stuff at L1. We already have something planned to put at L1, and that is we're planning to put a space station. The United States has a space station planned for L1 so that we can sit there and with very little rocket fuel at any time we want just hop off to the moon. We just spend all our time there. Then you want to go to the moon, you can go to the moon like this or like that. They're planning to build a space station. It's insane, in my opinion, to do such a thing, because if you want to go to the moon, the best thing to do is take off from the Earth and go to the moon. There's no reason to waste any time here. Just because there's a hotel here doesn't mean you should stop. You should just go from the Earth to the moon. Anyway, so this is a very important diagram. It's relevant for Jupiter, and it's Trojan Asteroids. It's relevant for Earth Moon, and it's relevant for the Gaia. Also, guess what? When the Chinese launched a satellite and put it on the back side of the moon, how do you communicate with a satellite, with a lander that has landed on the back side of the moon? What do you do? Well, of course, you put a space station right there to transmit the data back. So the Chinese have a satellite sitting at L2. It's a cool diagram.
I'm sorry, I'm a little lost. I'm not sure what these L points are.
Well, there are 5 of them. And the word L means Lagrange. So there are 5 places in a two-body situation where a third body can rest without having to use any fuel to stay in that one spot, or hardly any fuel, because as you see, they're all pretty unstable places to sit. You can fall off at any one of these places.
So
But
what's special about those places that you can sit there?
If you can sit, you put a rocket ship there, and it sits there. You put a rocket ship like we did for Gaia at L2. You put a rocket ship at Gaia at L2, and it sits there. And you don't have to use any rocket fuel for it to sit there. Theoretically, actually speaking, you need to use some to keep it from falling off the edge. So Gaia can stay at L2 for years. It can't. If it went around the sun, then it would sometimes be nowhere near the Earth, so we would have a hard time talking to it. But Gaia is always near the Earth, so we can always talk to it. It's right up there. It's always right up there. So we just point our radio telescopes to it, and we say, "Hey, Gaia, what'd you find today?"
So are they just arbitrary points?
No, they're not arbitrary. Look how unarbitrary they are.
Right, so why are they there?
Look at the wells. Look at the gravity wells. Gravity well of the sun in this case and of the Earth in this case. You can see why they're there. The gravity wells have inflection points, saddle points, where the gravity of one balances the gravity of the other in some degree. You know.
So it has to do with gravity.
That's what the gravity. Those are gravity wells. In case it's not clear, and so the deeper it is, the stronger the gravity. The deeper it is, the closer you are to the planet. So
Could
yes.
there be more points?
No, that's it. 5.
That's it.
That's it. 5 points. Every two-body situation has 5 points. Yes.
Maybe it's easier to visualize L1, for instance, is between Earth and Moon, where the attraction from both is the same. So if you come from the Earth, if you reach L1, then after that the Moon takes over.
Right. In the old days, you went from the Earth to the Moon, Jules Verne, and you were weightless only when you got to L1. Then the Earth's gravity and the Moon's gravity balanced each other, and then you were weightless. And then when you got on the other side, you would be standing on the other side of the rocket. I think there's some old science fiction movies have that as
You push a button,
you push a button,
yeah,
and what happens?
and you get to the other side.
And you get to the other side.
Mm.
Okay. I'll be forced to accept that. Okay. So So Gaia exists at L2. Okay, this video is going to show Gaia. First it's going to show Gaia, and then it's going to start showing the stellar nurseries that Gaia is seeing. So suddenly the sky will be populated by different colored objects. And each of those different colored objects have their color determined simply by the fact that this is a group and it's green, and this is a group and it's red, and there's nothing special about red and green except for the fact that these are the green ones and these are the red ones, and they belong to each other. So when you see the colors, just think of them as groupings of things that exist together, were born together, and are currently creating stars for the first time together. So that's Gaia looking at the Milky Way as it floats in space. Now these things that you're seeing are the stellar nurseries that it has discovered. It's not as if we couldn't see these before. We just didn't know they belonged to one another because we didn't see their distance. And now Gaia sees their distance, and it says, aha, those of you there these particular stars are a grouping. So the sky is filled with stellar nurseries. That's ridiculous. Look at all the places in the sky that stars are being born. And now the camera pulls away from, because the camera can do that because we know where the stars are. So digitally we can simply pull out from this picture. And you can see the nurseries moving past us. And so now you get a definite sense of their cohesiveness. And now we're pulling out really fast. And now we're going to see an artifact of this situation. What we see now is everything seems to be pointing towards us. All the nurseries in the sky are behaving like a pinwheel, a piñata, and they're all pointing at us. And why would they point at us? What's special about us? And what's special about us is we don't know how to draw these accurately. If we drew these accurately, they'd remain in a clump. But since we don't know the distances of these stars really well enough, they spread out because of the uncertainty in our measurement. And so some are wrongly further away and some are wrongly closer. So altogether you get a stream that seems to be pointed in our direction. So that's what this artifact is. We always, when we look in our galaxy, we always see things pointing at us. Now we're seeing that grouping of stars, the stellar nurseries that Gaia was able to see, and now we're seeing it in the context of the Milky Way. And now you can see that while we saw a lot, we didn't see hardly anything at all. Just the nearby nurseries in our galaxy. Yes?
Is this connected with the Radcliffe Wave, or is this completely separate?
No, this is the same data, except that these, and I'm going to say women, although I know only one of them is a woman. These women found the wave among all of this. They found a group of stars whose distances were accurate enough for them to draw this line between them.
Are the nurseries in the wave, or is that
Every one of those red dots that you saw in the Gaia wave is a nursery.
Okay.
So now look at the Milky Way. And now, since you've now got see, first I tried to show you nurseries with my old software, where I tried to show it to you like that. These are the same nurseries. Okay, these are the nurseries that I showed you 10 years ago when you were here in this class, the one or two of you. These are the nurseries that I showed you. But then Gaia came along, and instead of this set of nurseries, we now have, so that's the same set of nurseries, more or less, but now we see a lot more. And we also only see them close by. So So when we try to get a sense, I said 400 billion stars. Okay, that's what we're working with. How do we understand 400 billion stars? Well, for one thing, this is pretty impressive, and it's a much smaller number. Maybe 400 million stars in this. And yet, there's stars being created in this nursery. So let's see more what a nursery looks like. So you've looked up in the sky and you've seen the Orion Nebula, there, the Orion constellation. The constellation of Orion, it's his head, armpit, that's his Betelgeuse, where it might blow up, okay? But over here is the belt of Orion, and down here is the sword of Orion, and there is an Orion Nebula there, which is a stellar nursery. This object is 1,500 light years away. 1,500 light years away is close by. 1,500, so that's 1,500 light years away. The Milky Way is 100,000 light years across. So this constellation is very close by.
It's 400,000.
What?
I thought the Milky Way is 400,000.
No, the Milky Way is 100,000 light years across, and the number of stars is 400,000.
Ah,
So there are two stellar nurseries in this picture. One of them is Orion, the Orion Nebula, and the other one here is the Horsehead Nebula, and we're going to visit the Horsehead Nebula. So it's really next to one of the stars in Orion's belt. I'm zooming in on it slowly. This is what I'm interested in right here. This spot right there. Zooming in some more. There it is.
you're interested in the notch?
I'm interested in the notch, but what I can't do, see, it's not a notch. The name of this nebula is the Horsehead Nebula, and what I can't do without screwing it up is try to rotate it, but I'm going to try. Turn your head upside down for a second, and you'll see that that is the head and the neck of a horse. This is the Horsehead Nebula. This is a star-forming region right there. Why is it dark? Because you can't see through it. There are stars beyond there. There are stars inside of there. But there is gas that over millions and tens of millions and hundreds of millions of years, because remember, 100 million years isn't very much time when we're talking about billions and billions of years. So if I say 100 million years had something to do with the formation of this, then you would go, well, yeah, that's recent, isn't it? So recently, this cloud came together and became so dense that it shrouded the stars behind it and essentially hid from view the business, its business. And its business is making stars. And we can see it. So this is just to give you a sense of where this is in the sky. So when you look up and you see Orion, and you can see the belt of Orion in the sky, because it's not hard to see. Look, there's the ground. You can see the ground. See, there's the ground. This is at 12 o'clock tonight. You look up in the southwest, which is, get on your roof, look down the street. If the sky is clear, you can make out Orion sometimes in New York City. If you can, make out the belt. If you can make out the belt, there's a star-forming region right there. But what I'm going to show you a star-forming region, but what I want to give you a sense of is how many there are close by. So let's see if I can do, this is a star-forming region. I was going to show it to you later. I showed to you this to you before. This is a star-forming region. It is known as the finger of God, and it is also close by. And you can see there are other star-forming regions. This is a fairly large one, but not very large. You can see this one right there. Well, that's a star being formed, literally. That's a star being formed, and you see a little tail? Well, that little tail from that star is being blown away by the stars that are up there. There's a star up there that's blowing a wind that's creating this sort of effect in this direction. The stellar wind blows the gases away, and they get a chance to form only in the very last minute, but most of the gas that they were forming from has been blown away by that star up there. So, finger of God, star-forming region, stars being made inside of here. Normally in outer space, we have, in this room, we have 10 to the 23rd molecules per cubic inch. Here, the number is more like 1 per cubic inch. As you get closer, the number is more like 100 per cubic inch. As you get inside of here, it becomes tens of thousands of molecules per cubic inch. When there's enough of them together, there's enough gravity to form a star and solar systems. Yes?
When you're saying wind, it's not like a gust outside. It can't be. It's millions of miles distant each from each. So when you say there's a wind that is exacting or creating this sort of circumstance,
It's a wind. It's a wind. The difference between what your concept of wind is and my concept of wind is that I can have a wind with just 1 million molecules moving towards you, and that's a wind.
Okay.
You need 10 to the 23rd before you think it's a wind. Nevertheless, if there's a group of molecules moving in the same direction at more or less the same speed, it's a wind. You just need enough space. Well, space is very big. So with a lot of space, there's a giant wind out there, a wind that is so strong that it has more molecules in it than the sun itself has atoms in it. Winds that are hundreds and hundreds of solar masses heavy, blowing towards other things that are also solar masses, but they are more concentrated. So the wind blows off some of the star-forming gases, but there's enough wind to blow off a solar mass.
were we in the way, would we feel that wind?
We are in the way right now, and the sun has a wind. The solar wind. It is called a solar wind, and it blows past us every minute of every day. And the only ever time you hear about it is when the wind becomes strong enough and it causes the aurora. The aurora is when the solar wind blows down hard enough and deep enough that it can ionize the gases in our upper atmosphere, and then we see it. It's there all the time. 1 million miles an hour sometimes. Thousands of miles per hour other times. Per second. Yes?
The solar wind, and you're saying we get a solar wind from
From our sun.
star,
Right.
and it comes in a certain direction. And you said a solar wind is coming toward that. Now,
A different sun is blowing, a different sun's solar wind is blowing towards that.
It happens so that this solar wind comes in different directions, not one direction throughout the universe.
The solar wind is a wind that blows from our sun. It's its official name. And it blows from our sun, and it blows past the Earth and Mars and Jupiter and Saturn and Uranus and Neptune and Pluto, and even beyond Pluto. We know this because we've been there and we've measured the solar wind. And guess what? We've measured where the solar wind stops, because the solar wind is now more and more diffuse. It's filled with magnetic fields, which because the solar wind carries with it and is carried by the magnetic fields that link all the ionized particles in the universe together. So the solar wind and its magnetic field flying out from the sun eventually encounters the galactic the galactic magnetic field and the galactic environment, and at some point the solar wind is paused, and they call it the heliopause. The heliopause is where the solar wind stops, and we have passed through it. The humanity has passed through the heliopause, and we've measured it, we know where it is, it's around where we predicted it to be.
But where is the solar wind coming toward?
It's radial, it's going out everywhere from the sun. Where is it coming towards?
In other words, what you're pointing to over there, the solar wind comes from our sun?
No.
That's what I'm
This is
asking.
no longer, I'm going to call it a stellar wind.
Okay.
It's a stellar wind, and the stellar wind is from a star, a very strong, very luminous star that's off out of the picture, that is creating both ionizing radiations, in other words, just light that can ionize the gases that are made. These gases are inert. These gases are made up of literally just hydrogen molecules. A hydrogen molecule, H2, is sitting around in these clouds, H2, because most of the universe is hydrogen. So these clouds are mostly hydrogen, H2, with a little bit of some other stuff that makes it little black. They call that dust. That is in there, and it's being subjected to both the intensity of the light from that star and the wind from that star, the stellar wind. Yeah.
So that every strong star sends out this wind.
Every strong star sends out,
direction from-
almost every star sends out the wind. Stellar winds have come from every star.
And they went toward this star formation and impacted this star formation.
And they went towards this star formation and impacted this star formation. Right. Yes.
I don't know how come it isn't an inert star, and how is it that the stars generate winds when they
Okay. How come a star generates winds? Okay, that is a good enough question that if you were an experimenter and you had a good number of papers and grants associated with your name, and you were well known, you could easily get a few $1 billion to answer that question.
Oh, just let me write that down.
Yeah, but no, it's being done. It's being done. The answer to that question has bothered a lot of people, not just you, as to why the sun is creating a solar wind. Why would that be? Let's check it out. So they sent a probe to the sun. It's called the Parker probe. The name Parker Solar Probe. And the reason it's named Parker is it was this guy, Parker, who is still alive, who said, there's a wind coming from the sun. And people said, nah, you're wrong, not so, I don't get it, I don't believe it. He was right, the rest of the world was wrong. He got the probe named after him. That's what I call sweet revenge. And his probe is now circulating closer to the sun than Mercury ever goes. It's much closer to the sun. It comes into the sun, and then it's got sunshade, so it shouldn't boil up. And then it comes back out, sends its data, goes into the sun, measures the solar neighborhood. It can't get close enough that we would love it to get, but it gets pretty close, and it's figuring out all sorts of questions. The main one being, why is there a solar wind? So we've always known this answer. Yes?
Every Apollo mission measured solar wind and brought samples back.
Every what?
Every Apollo mission.
Every Apollo mission.
Yeah.
Yeah, every Apollo mission captured solar wind and brought it back to Earth.
On an alufoil kind of thing, it's like this flag next to the American flag on the first Apollo mission.
It was a flag
It was
next
the
to,
solar wind experiment.
it was a solar wind collector that sat on the moon while they were out walking on the moon.
They brought it
And
back.
they brought the collector back from the moon to see what the solar wind was made out of.
It's just like interstellar fart.
interstellar, it doesn't, no, a stellar fart, not an interstellar fart. That would be nice. We'd like to get a couple of interstellar farts, but no, a stellar fart. Yes.
Are all suns made of the same thing?
Yes and no. Are all suns made of the same thing? Yes, yes, and no. They're all made of hydrogen mostly. They're all made of helium mostly, and then that's mostly it, except for the traces. And the trace elements are what makes the difference. The trace elements are things, look around this room is filled with the trace elements. This room has, if we didn't have the trace elements when our sun was being formed, this room would be filled with hydrogen and helium gas. And there wouldn't be a planet here. The fact is, the trace elements are the things that the planets, especially the terrestrial planets, are made of, and the things that we are made of. If the sun wasn't a third generation star that had been created from the explosions of previous stars, which created the trace elements that was inside of our star, we wouldn't be here. So some stars have no trace elements, and they have puny planets, nothing interesting to speak of, because they don't have silicon, they don't have iron, they don't have any oxygen, they don't have nitrogen, they don't have any of those things. These things were built inside of stars, spewed out in a giant fart, and then recreated in a new star. So no, all stars are not made of the same thing. In fact, all stars are different, but only in the trace elements. And you literally, hundreds of people make their livings entirely worrying about what stars are made of, despite the fact that we know they're made of hydrogen and helium. If you look at the spectrum of our star, you can see all the trace elements in our star. That's how helium was discovered, not on Earth. It was discovered on the sun. It's called helium because it's helios, which means the sun. So when they went looking at the spectrum of the sun, they saw an element they didn't understand. Because you could take any element in this room and ignite it into fire. It produces a bright light when you heat it up. You look at the spectrum, you say, I can see that's iron. The lines of iron belong over here on the spectrum. There was one line they didn't see anywhere on Earth. What is that line? We never saw it before. It was helium. So they can see all the lines on the spectrum on Earth. They take all the elements, they burn them, they heat them up, they look at the spectrum. Same lines are on the sun. Then you go out and you look at the different suns in the universe, and some suns have more or less of these elements. And you can say, well, gee, if it has less of these elements, it must be a star that was formed a long time ago, before the universe was filled with these elements. Because 10 billion years ago, and there are stars that are 10 billion years old, these elements weren't floating around in the universe. You had to have stars that exploded many times before these elements were free to accumulate in the star system that we are. So no, all the stars are different. You get 3 extra points for that question. It's fantastic. Yes?
And does the spectroscopic analyses that are being done for stars here, there, and everywhere, do they reveal more than what we have now, the table of elements? Do you occasionally have, oops, there's a new guy, there's a new element?
Yes, so yes and no. Yes, there are new lines that we've never seen before. And no, because nobody in their right minds thinks that there's a new element to be discovered in a star.
Oh.
Yeah. In other words, there's 92 elements, period. There's some more that we've created that from radioactivity and stuff like that, but the ones that are hanging around today anywhere in the universe, not being made, but simply sitting around, there's 92 of them, that's it. So the only question, if you see something in the sky that you don't recognize, you don't go ahead and think, well, maybe that's a new element. But you go ahead and you sit down and you figure out, how could that line exist? And sometimes the way it exists is really magical. Let's take oxygen. Oxygen has, let's say, oh God, I don't know my chemistry. Anybody know how many, where it is on the periodic table? Number 8? 8 on the periodic table?
That rings a bell.
Right. I think so. It's possibly 16, but 8. Okay, so it has that same number of electrons, okay, in orbit around. Let's say it's 8. God, when I edit this, I'm going to put the right number in. Okay, it's embarrassing that I don't know this, but let's say 8 electrons. Okay, now if one of those electrons is removed from the atom, and then it comes back into the atom, when it drops back into the atom, it will produce a ray of light that becomes the spectrum of the oxygen atom. That's how it's produced. When you ionize the atom, the electron is removed. When it drops back and releases the energy that it had when it was all the way out there. That's the spectrum. What happens if it doesn't drop all the way back? What happens if it doesn't drop all the way to the deepest level of the atom? What happens if it drops to maybe the second orbital, or maybe the third orbital, or the fourth, or the fifth, or the sixth, or the seventh, or the eighth, or the ninth orbital? Because all of those are okay. This electron all the way out there is still part of this atom. It's just loosely bound. So when this electron moves from here to here in its energy state, this is between number 34 and number 33 levels above the surface of the deepest orbital in the atom. And nobody thought about calculating what this spectrum of this particular transition would be. And when they do, they find the missing element that you're talking about. So they'd have to do an awful lot of quantum mechanical calculations to figure out what the various possibilities are for atoms to produce light. And there are a lot more than we thought initially.
And isn't there an O3?
O3 is simply 3 oxygen atoms together in a molecule.
Right.
And I'm not talking about molecules, I'm talking about an individual atom and individual electrons in the atom. And of course I skipped a couple of words that you may not know, like orbital. Who doesn't know what I meant by orbital? We have one hand. Anybody else who doesn't know what I meant by orbital? The word orbital, in the old days, you drew an atom, okay? You drew an atom, and you drew the atom of, let's say it had 8 protons. Well, then the 8 protons, you drew 8 little electrons around it. But if you realize that if you had 9 protons, well, then there'd be 8 plus a 9th in the second orbital. And then you have to fill all of those with, 10 protons, 10 electrons, and so on. So you fill the second orbital until it fills up with the proper number you can have no more of. And then the third orbital. So all atoms have allowed places where the electrons can be, and those are called orbitals. And while you generally only fill the first orbital, the second orbital, which is unpopulated, can still be filled with things. They're just loosely bound and tend to fall off the atom, but they are there. They're possible. Anyway, any other questions on that? So I wanted to show. So that was the Horsehead Nebula, and now I need to show you the Horsehead Nebula. So the Horsehead Nebula. So we're going to sort of zoom in on this. So this is wisps of gas surrounding the Horsehead Nebula. So there's the Horsehead Nebula. Now you can see it better. It's been upright. Now you can see it as a horsehead. There are 3 kinds of gases here. There are ionized gases here. And there are gases, look, let's say 2 kinds. This gas has been ionized, let's say, from stars here or stars here. This gas is being ionized by light from other stars. But this right here is not being ionized. That's a cloud. It's a dense cloud. You can't see into it because it's so filled with dense gas and dust. So, another view of the Horsehead Nebula. This really gives you a sense, aha, so there really is just gas and dust. I can see now. There are the stars. Are these stars here? Are they inside or outside? Well, these are outside. But I now can see the Horsehead for sure. So there's, and of course this is one of the first nebula ever discovered. And then there's a close-up from Hubble. Now you can really see that it's beginning to lose its horse-headedness. It's got wisps. Now we're beginning to see the stars inside of it. These stars are inside, being made inside of this nebula. Hundreds of stars being made inside
These
this.
are photographs as opposed to...
These are photographs. Hubble.
representation.
This is no longer representations. These are photographs. Now, they are not taken lightly. They are often used. They are often combined. In other words, one photograph in one wavelength is combined with another photograph at another wavelength with a different exposure time. So you can't get these photographs by training your camera on the Horsehead. You have to have technique, but it's still not an artist's conception. It's real.
The colors aren't added? Or?
The colors may be a little bit false, but they're generally intended to be correct. This color here is real. That's the real color. Now this is guaranteed to be false color. Look at that. Now you can see the cloud. Now it's no longer, Laird says it's a cloud. No, you can see clumps of cloud here. This exposure is very well done. And it's done in various wavelengths. So many pictures have been combined to give this effect. You can't take this picture just by snapping the picture. You take it in various wavelengths. Remember, yes?
How does GAIA identify nurseries? Is that done in like processing later to...
I don't know how GAIA is determining nurseries
It's not looking at gas,
because GAIA is not looking at gas. Okay? So there is a
proximity or something like that.
GAIA is looking at something that is not gas. It's not designed to do that. So there is more there than this conversation. You're absolutely right. This is a picture of Orion, and this right here is where we're talking about the Horsehead Nebula, right there, right there. 3 stars across the belt. Horsehead is right there. So there again is the 3 stars and the Horsehead right there. And now for the last and final thing I'm going to show you, this, I love this. This is a movie made from real data. This is zooming in on the Horsehead Nebula. So there's Orion. That's the Archer. The 3 stars. You can see where the Horsehead is. Star forming region. You can see the stars within it. Now we superimpose that picture you just saw on that. And just this is one of the hundreds and thousands of stellar nurseries that are right part of our literal stellar neighborhood. This is a neighbor of ours. We were born in such a cloud 4.56 billion years ago. That was a home for us. See you next week.
Doesn't have anything to do with dark matter.
No, again, dark matter has very little to do with star formation per se, although it certainly has something to do, dark matter at that scale certainly exists and can have something to do with it. But there's dark matter between the clouds as well. Is a clump of dark matter responsible for the collapse of that stellar nursery? Does it have anything to do with it? We actually don't know the answer.
And
There
does
could be
it have
clumps of dark matter. We don't know the answer to that.
And it has nothing to do with the shape it's formed? Maybe the dark matter is creating that shape somehow?
It's-
Making it bulky, or making it skinny, or making it something?
If somebody said that next week, I wouldn't be surprised. If somebody said the dark matter is responsible for the shape of the nebula, then I wouldn't be surprised. But I would be surprised because that would mean that dark matter clumps. And dark matter is not known to clump. It's known to sort of clump at the level of galaxies. Whether it clumps together at the level of stellar nurseries is not clear. Do the attendance sheet.
You said that Gaia also looks for asteroids that may be headed
Towards
in the
us.
direction of Earth.
Right.
To what end?
So we don't get hit by them. So when we find one,
If it's headed to, we're not gonna, is the idea that maybe we can change the direction of an asteroid?
the idea is that maybe we can definitely change the direction of an asteroid.
I see.
Are we getting hit?
Well, yes, tomorrow. Take cover.
Near your desk.
Right, right. No, I have no idea if we're being hit. We were trying to make sure that we don't get hit. And we hopefully will be able to, if we have enough time, we'd be able to deflect it.
Do we have any sense of the size of the asteroid that hit the Earth that killed off the dinosaurs?
Yes, we do. I think it's in the neighborhood of 10 miles in diameter.
Is that something we think, if that came, is that something we think we could change the direction of?
Given enough time, we can do anything, but we have to have enough time. So how do you change the direction of something that's 10 miles wide? You do it. You spend 100 years doing it.
Oh,
Okay.
And the Alduvi Gorge, which is a huge crater formed by an asteroid that fell down millennia ago.
I'll take your word that it's a crater. I forget.
Well, it is.
Okay, fine. I'm just saying there are a lot of craters on the Earth. I just didn't know that that one by name is. I'll accept it. It is, okay.
How about the one in Siberia?
Yeah, and there's one in Siberia. Yes, but anyway, what's your question?
So in Alduvi Gorge, it wasn't, the asteroid was hypothesized to be no bigger than 50 miles big, and yet it caused vast, problems.
Right.
Huge disorders.
50 miles is pretty big for an asteroid.
I did.
50 miles wide is big enough to wipe out most of the life on Earth. So no, probably 5 miles. I don't know how big this one is that you're talking about, but yeah.
Alduvi, they hypothesized 10, 20 miles big.
Okay, I'll look it up.
It's too much land.
Yeah. Right. Anyway, so see ya.
Thank you.
Thank
Welcome.
you. Thank you.